Okay, so one time I told you if we have a first order differential equation like this one, here the unknown is x of t. So x of t here, this is the unknown. You have this is the equation. A and u are known and they are constant values and they are known A and u. If you have a differential equation like this one, the solution is so this is the solution where x of 0 is actually the initial value and it should be given to you. X of infinity is actually should equal u divided by a and or tau times u, where tau is actually 1 over e. So 1 over e, we call it tau. Tau is actually time constant. This is the name of tau, time constant. Okay. So this is the solution of this equation, and you can see the solution is, or the way you can see the solution, this part here, this part is actually, this is the steady state response, okay? And this one here is actually the transient response. Okay. Why? Because simply at when e to the power, this part here actually goes to 0, becomes 0, and t increases. And this is the transient. So we have only this transient response, we have only at the first time, for a very short period of time. After that, it disappears, and this is the steady state solution. Okay. This is the equation. One way to see this equation this way. There is another way to see this equation. So I will do very simple algebra manipulation, and I will rewrite this equation. So actually, I can rewrite this equation this way: x of equal x of 0. So I need one part that has x of 0, and the other part has x of infinity. So this one e to the power of negative t divided by tau plus x of infinity times 1 minus e negative t divided by 10. Okay, so it's the same equation, but I did very simple manipulation to it so that I have one term that has x of 0, the other one has x of infinity. Why you did this one? Because I want to see this part now. This is the contribution, or this is the impact of the initial value. Okay, so this is the impact of the initial value. So as you will see right now, if you have resistance and you have a capacitor this way, and then I have here Vs, okay? So actually here, x of 0 is actually the initial voltage here, V0, the initial voltage, okay? So this part is actually the impact of the initial voltage. X of infinity, which is is actually Vs, because as I told you last time, in a steady state, because the input here is DC. In a steady state, actually the capacitor here becomes open circuit this way. And actually the voltage here Vs. So Vs is the steady state or the impact of the battery here. So anyway, the reason I read this equation this way, because I want to see this part, this is the impact of the initial value. Initial value here is actually the initial voltage of the capacitor, as I will explain. Also, this part, this is the impact of Vs, the battery on the solution. Okay, so now, so again, number one, if you have an equation like this one, this is the solution. Is that okay? We agree on that. So what I will do right now is, or the purpose of this chapter is to study two circuits. So that's what we do in this chapter. I want to study circuit. If you here have a resistance and then capacitor, and then you have here a DC voltage Vs. Also, if you have resistance and then you have inductor this way, and then you have here Vs. Okay, so this is the purpose of this chapter, just only to study these circuits. Okay, so you will see right now what I will do is I will use Kirchhoff current law, Kirchhoff voltage law, so that I will get from this one, I get equation like this one. Same thing here. From this one, I will get equation like this one. You understand what I'm saying? You will see right now how I will do it. Okay? That's why I started from the mathematical part. If I have an equation like this one, I can solve. So you will see right now how, if you have a circuit like this one here that has a capacitor, how you will get the equation like this one. Once you have this one, okay, so I can solve it. I have the solution here. So that's what I will do now. Same thing here if you have a coil. And this is all what this chapter is about. What this chapter is about, if you have RC circuit, this one is called, we call it RC because we have R and C here. This one is called RL circuit. How can we study the response, or how can we analyze this circuit? Okay, before so let's see. So now the question is, I will start for sure. I will start with this one here. Again, all what I told you is I will try to see if I can Kirchhoff current law, Kirchhoff voltage law, whatever I will use, so that I want to get an equation similar to this equation here. Okay? And once I have this one, I can solve it. Now I have the solution. That's it. It's done. Okay? Same thing I will do here. So let's start with the first one here. But before I start this one, I think there was some figures I want to show you here about what is the impact of tau. So here tau, you call tau here is a tau here, which is 1 over A. You call it time constant, and this is A here. Whatever number you have here, 1 over this number is tau. Okay. What is the impact of this tau? Okay. So I will choose some figures here just to understand what impact this tau has. Yeah, so as you see here, if you have here e to the power of negative t divided by tau, okay? You can see here as tau, because I just want to remind you, in last time I give you the final conclusion. The final conclusion is, if you have a resistance and you have a capacitor this way, and now I'm giving you more details, okay? So this is the current. The current will become something like that. There is a current only for a very short period of time. There should be some current here, very short time until the capacitor is charged. Okay, so this is I, and this is VC, and this is IC. So this one actually here is gonna go this way until it becomes, and this is actually here equal to VS. Because at this part here, I told you this is a transient, and this part here is actually the steady state, as I told you last time. As you see here, at the steady state, you can see current is equal to 0. The voltage across the capacitor equal to Vs. Okay, that is because I told you in steady state the capacitor actually is open circuit this way, and because it's open circuit, there is no current. Okay, and the voltage here across it is actually equal to Vs because there is no current here. There is no voltage drop. Okay. So now I want to see what is the impact. So I will give equation right now for this case. You will see the equation is actually similar to this one here, but I just want to show you what is the impact of tau. If tau is large or tau is small, what impact it can have here. Actually, the impact is, look here, guys. So here it's gonna be something. So it's gonna, as you increase tau, it's gonna take more time. So the transit time is gonna be bigger. It's gonna take more time. Same thing here. As you increase tau, it's gonna take more time. As tau is shorter, small, it's gonna become this way. Okay. So if you go this way, you actually increase tau. So I just want to tell you what is the meaning if you increase tau or not. So this actually shown here in this figure. So here, because this term here, so if I go back here, because we have here the equation, the transit equation, yeah, this equation here. So this term actually is this term here is going to control the transit response. Okay, so we need to look at this one here. So if you see here, yeah, as I told you here, you can see it's going to take more time to charge the capacitor. So as tau increases, so it's going to take more time to charge the capacitor. So the transit time is bigger. Same thing here, it's going to take more time until it reaches to VC. That's it. This is the meaning of it. Okay. Yeah, this is the figure. This is the same figure I have. The same figure I did before, but here you see what I did in this figure here. I assume the initial value is 0. So here we assume here when I told you this is the voltage. Actually, I assume the initial value is 0, but it may not be 0. We may start from a certain voltage. The capacitor has some voltage, so it's gonna be the same thing, but I'm not gonna start from 0. I'm gonna start from here, okay? Because of the initial value. This is also what is shown here. Yeah. So this curve very similar to what I did, but this is the general one. What I did when x of 0, as you will see shortly, is actually the V capacitor, the initial value in the capacitor. But anyway, same thing here. This one is similar to what I explained before, but what I explained before, it was we started from, yeah, this one here we started from 0 because this is the initial value. Same thing here. Anyway, so let's move to the so again, the conclusion. What I want to say here, guys, the conclusion is if you have this equation this way, what is the impact of tau? That's what I want to say. If tau, the larger tau, is going to take, the transit time will be more. It's going to take more time. That's what I want to say. Now I'm going to return to my point. My point is, given us, if you have a circuit like this one here, R and C, and then we have here VS, and we have here IC. This is the current. And then we have the voltage here VC. Is that okay? I want to write an equation for this one. I can simply use Kirchhoff voltage law. Okay, let's write the equation. So the equation here, if you write Kirchhoff voltage law, negative VS plus ICR, okay, plus VC is equal to 0. But there is one more thing here. You know the relation. You know here in case of capacitor, there is a relation between I and VC. Okay, so here IC is equal to C dVC by dt. You know this one, okay? So all what I'm going to do here, I'm going to take this one here, I'm going to put it here, so that after that you see here I have minus VS plus RC dVC by dt plus VC is equal to 0, okay? And then I'm going to rearrange this equation. So this equation becomes, after I'm going to bring this one here, I'm going to divide by RC. So after I rearrange this equation becomes dVC by dt, okay, plus 1 over RC, okay, times VC equal to VS divided by RC. Is that okay? So now, if you compare this equation with the equation I said right now here, it's exactly the same thing, okay? But what is A and what is U? So here, the original equation was dx by dt plus A, x should equal U. So this part actually should be A, makes sense? And this part actually should be U. Okay, so now it's the same equation. And the unknown now is actually VC. This is the unknown. Okay, so if you have this equation, do you have the solution? For sure, yes, I have the solution. Because this equation actually is similar to this equation. And what is about tau? What is tau? Okay, so actually tau should equal 1 over A, which is 1 over C, which is actually RC. Okay, because this is A. 1 over A should be RC. This is tau. Okay? So any question so far? It's easy, right? So here, yeah, this equation is similar to the equation I explained before. That's why I'm going to use the same solution. Okay, that's why I'm going to use the same solution. So let's see the solution we have here. The first one at least. Let's start with the first one here. We have x0. X0, this is again the unknown is the voltage across the capacitor. So x0 here is actually, let me write this equation. So the equation we had before, x of t should equal x of 0. Again, x here is the voltage across the capacitor. This equation can give me the voltage across the capacitor. X of 0 minus x of infinity, okay, times E minus t divided by tau plus x of infinity. That's okay. So x of 0, this is something, it has to be given to you, or you need to figure it out. This is not something in the equation here. What is the initial value for the capacitor? So if the capacitor is going to start charging and the initial value was 0, so x of 0, this one is 0. Okay? So x of 0 here is actually, in our case here, is the voltage of the capacitor at 0 in the very beginning. What was the voltage of the capacitor? Okay? So in this one, I'm going to call it V0. So I need to find it. Okay. Okay. What about x infinity? I told you x infinity is actually u divided by A. Okay. Or tau times u. It's the same thing. Okay. So in this specific case, this part is u. Don't forget, this part is u. So here, actually, this one should equal to RC times Vs divided by RC. So actually, it should equal to Vs. Which makes sense. I don't even need to calculate it. I calculate it, but you don't need to do that. Why? Because x infinity is actually the steady state solution, a steady state. And I already know in a steady state, the voltage here equal to Vs. So already I know that. You got what I'm saying? So I don't even need to use the equation here. I don't need to divide u by E, but just I did it to show you it is actually equal to Vs. So now I can say Vc, the voltage across the capacitor, should equal to V0 minus Vs times E of minus t divided by tau plus Vs. Yes. Yeah, this is the solution. So again, guys, very simple. So if I have this circuit here, okay, so and I wanna find the VC, the voltage across VC. This is the solution. Is that okay? Be careful. I'm saying this is the solution for this exact circuit. If the circuit is different, you cannot use this formula. This formula for this exact circuit. When you have C, when you have R, and you have voltage source, it's DC, not AC. If you have this exact circuit, this is the solution. Is that okay? And again, if you look at the solution, so this is the steady state solution, and this is the transient part. Okay? So this part is only for a short period of time, transient. Is that okay, guys? Any questions? I can also rewrite this equation similar to what I did before, so that I need V naught to be in one block and one side, and Vs will be in another term. So the way I can do it is actually Vc should equal V naught E minus T divided by tau plus Vs times 1 minus E negative T divided by tau. I didn't do anything. I just took these two together and this one alone. This is also, it's the same thing, right? It's the same solution. But I wrote it this way because this one can take me something different. This one can tell me this is the impact of the initial, this is the impact of the initial voltage across the capacitor of the solution. And this part, this is the impact of Vs, the battery Vs. Okay? So these two solutions, these two equations are solutions for this circuit. Okay, this is number one. Number two, this format of this equation can tell me this is the transit part, this is steady state part, and this one can tell me this is because of the initial voltage. This one can tell me this is the impact of the battery, Vs. For sure, if the capacitor was not charged, okay, there is not any charge in the capacitor, so actually this term should be zero, right? Because the initial voltage is zero. Okay, whatever it is. Any questions? Okay, guys, any questions? Okay, now I have 3 or 4 examples. I think 3 examples. All of them are the same idea. What idea it is? The idea is, look here. I need this, the circuit has to be in this format. I should have a circuit like this one, and then I just apply the solution to it. Okay, you will find sometimes this is not the case. Sometimes this circuit is different, so I have to do something. Okay, for example, to be more specific, for example, sometimes I have a resistor here, another resistor here, and have a battery here, and then I have a capacitor this way. This circuit is not exactly like the other circuit, because here I have two resistors here. In the other circuit, we have only one resistor. Okay. So in this case, that's very easy case. I can just add these two together. So now it becomes like R1 plus R2, and then you have a capacitor, and then you have here a voltage source. That's it. Is that okay? This is one example. In another example, it was completely different. It was something like you have a resistance here, and then you have something like that. Okay, and then resistance, and then a capacitor. Oh, how I get this is completely different from the original circuit, right? Okay, that's very easy. All what you have to think is to Thevenin. Okay, I know you love Thevenin. We're getting it on something. So what I can do here, we can calculate Thevenin to this part here. Once you calculate Thevenin to this part, now we're okay. So we have a resistance here R Thevenin, and we have here V Thevenin this way, and then we have a capacitor this way. Yeah. So now the circuit becomes exactly similar to the circuit. I know the solution. Is that okay, guys? So this is the first thing. Okay. The other thing also, how I can know, you will see the example, but I'm giving you what you will see in the examples. Okay. The first thing, the circuit has to be similar to this one to be able to use this equation. Very simple. This is number one. Number two, I need to find the initial voltage. Initial voltage. Okay. Sometimes the initial voltage is given to you. Sometimes you need to figure it out. Okay. I will leave this to the examples. You will see how we can do it. Okay. Sometimes the initial voltage is just given to you. Okay. Just use it. Or sometimes you will figure it out. I will tell you how. Okay. So let's now go to the examples. Yeah, so this is the solution I found. This is the solution we found. If I wanna do the solution, it will become something like that. We started from V0. If V naught here is 0, so you're gonna come from here, but you started from here. There is something also I didn't mention here. So this equation actually is gonna give you the voltage across the capacitor. Okay, so yeah, I wanna keep this one here. So this equation here, this one gives me the voltage across the capacitor. Is that okay? Now, okay. Now I have the voltage. Can I get the current? Can I get IC? For sure you can, because you know already IC is equal to C dVC by dt. All what I have to do, I have to take this equation, put it here, differentiate it. You can accept to get I. So if I give you V, you can get I, because there is a relation between I and V here. You can accept. If you do that, if you take this equation and you differentiate it, okay, keep in mind Vs is a constant value, so the differentiation is 0. Because again, we study this specific case where Vs is constant value. If you do that, you will find IC equal I naught. I'm going to tell you what is I naught. E to the minus T divided by 10. So what is I naught? I naught should equal Vs minus V naught divided by R. This is the second equation. I can in quizzes in exams, I can give you these two equations. I'm totally fine with that. Okay. But what's important, you need to know how to use it. So I in exams, I will give you this equation. Also, I will give you this equation. Okay. So this is the voltage across the capacitor. This is the current. This is the current here. Okay. And I naught is Vs minus V naught. V naught here is actually the initial voltage across the capacitor divided by R. Okay. So actually it is like, remember, this is Vs is here. Remember, V naught is here. So this is, so here I know I can calculate it from here. It's the voltage across in the very beginning, the voltage across the capacitor divided by R in the very beginning. Because this is at time 0. Because at time 0, this is the voltage of the capacitor is V naught. But it's gonna change after that. After time 0, it's gonna change because it's gonna the capacitor started to charge. Okay, guys. So make it very simple. So if you have a circuit like this one, okay. So you have this is the voltage across the capacitor, and this one is the current across the capacitor. Okay. If you draw these two, if you want to draw them, it becomes similar exactly to what when first I give you the conclusion. It's the very beginning. Okay, it's exactly the same thing. So here you start from I naught, and then you go to 0. This is for the current. For the voltage. The voltage, I'm gonna start from V naught, the initial voltage across the capacitor, and then it's gonna go up this way, okay, until it becomes Vs this way. Is that okay? This is I started with this one because this is the final one. Any questions? Okay. So again, for the last time, so again. If you have a circuit like this one, C and R, and this one, this is the conclusion of everything I explained. If I have a circuit like this one, so actually VC should equal to Vs plus V naught minus Vs times E minus T divided by tau, and tau here is actually RC. Okay, and you know tau is gonna control how much time it takes to charge the capacitor. Okay? Also, IC is actually, you know how I calculated it, but I will give you the final answer. I already explained how I calculated it. So here I know E minus T divided by tau, and actually here I know is actually equal to Vs minus V0, the initial voltage of the capacitor, divided by 1. That's it. So now I will show you using these two equations. I will solve the coming examples. Is that okay, guys? Easy, right? So the coming example, I will use this equation. However, there are two things. Okay, number one, I have to make sure that in the questions, I have to make sure I have to work in this circuit. If it is not, if the circuit is different from this one, I can't use this solution. Okay, this is the first thing I will do in the example. The second thing I will do in the example, if the initial voltage is not given to you, I will let you know how can you find the initial voltage, because you need it in the solution here. We have V naught here and we have V naught here. Is that okay? So let's go to the examples. And this is I told you for test one, the third question in test one will be similar to one of the examples I will teach you. Okay, about this one. So let's start with this one here. This one I took it from the textbook. So let's start with this one here. Yeah. Assuming, okay, let's start. Okay. I'm gonna start with this one. I will leave this one to the end. So let's start with this one. So I give you a circuit like this one here. Let's see how I give you R1. So you have a switch. This is a switch. This switch can connect it to one or two. Okay. So here I give you everything. I give you R1, I give you the capacitor, I give you R2, Vx1 and Vx2. Is that okay? Now, look what I said here. What I said, after being in position 1 for a long time, this is very important. What it means, after being in position 1 for a long time, okay, the switch now is going to move to position 2. So it was when the switch was. Yeah, this is how was the circuit. The circuit was connected this way for a long time. Is that okay? And then at time 0, at time 0, I moved the switch from here to here. Okay? So how this can help me? Yes.
Your initial voltage is VS1.
Yes. So this can help me to know to get the initial voltage. Because when I tell you long time, what it means when I tell you long time, what it means?
It's charged.
It is in a steady state. That's what I mean. Long time, it doesn't mean 5 years, 10 years, can be 1 minute. So I'm already in a steady state. This means it's sharp already in a steady state. You got what I'm saying? So here I told you this was before time 0. Okay. So here before time 0 it was something like that. This capacitor was already in a steady state, and you already know if this capacitor in a steady state, the voltage across it equal to VS1. So this is the initial voltage. You got what I'm saying? So this is the initial voltage. So the initial voltage is the steady state before we connect the switch. You got what I'm saying? So it was in this position for a long time. So this one was actually in steady state. That's why the voltage across the capacitor equal to VS1. Okay, now we will start. Now I'm going to connect this one to here. I'm going to connect it to number 2 here. Okay. And the initial voltage, I already know the initial voltage. So now if I come here now, I will connect the switch this way. This part is disconnected. I know this is one thing sometimes to confuse some students. So look here, guys. This part is disconnected. It has nothing to do with the circuit. I already disconnected. You got what I'm saying? So this is my circuit is here. Okay. So now I'm gonna start. Once you connect the switch this way, so this is how the circuit looks like. If this circuit similar to the circuit, I already know its solution. I can twist it a little bit. Why? Because the circuit, I know it has only one resistor, but this one has 2. Yeah, but these 2 resistors are in series, so I can actually add them together. Okay, so this part here actually is equivalent to this part. So now this circuit is exactly similar to what the circuit I calculated the solution for it. Okay, but where this resistor here is actually equal R1 plus R2, which is 10 plus 20, which is 30. You got what I'm saying? These 2 resistors are in series, so I can add them together. Now this circuit here becomes something like that. I already know the solution of this one. Okay? Number 1, I know the solution of this one. Number 2, I already know the initial value because I need it. Okay? All what I will do after that, just I'm gonna plug in this equation. This is the equation I have. This is the solution VC. I know everything. Okay? I know VS2, which is this one here, VS2. I know the initial value, which was VS1. I know VS2. I know RC, R times C, which is tau. Tau is equal RC. I know everything. After you just plug everything in here, so this is the final equation I have. This is the voltage. This is the relation between voltage and time with the capacitor. You can see this is a steady state solution. This is a steady state. So after transit, it will be 20. 20 actually is VS2. So here, after transit should equal to VS2, which is 20 here. Makes sense? And this is the transit part. This part will disappear. When T is high, when T has some high value, this part becomes 0. Because E to the power of negative high value is 0. So this part is going to disappear. Okay? So using this one, I can actually, so here, you can see this part is the transit part here, okay? And we have the steady state part. So if I, yeah. So as I told you, we are gonna start from V0, whatever the value is. We're gonna go up and then steady state here. Okay. So this is the transit part is here. Okay. And this is the steady state is here. So that's why we increase here because of the part, the transit part that has E. Okay. So anyway, same thing. So now I have V. Now I can get I. Okay. I told you I have a formula for I. I give it to you. E negative T divided by tau, which is 3. Okay. So it's the same like this one. Because this one also E to the power of negative T divided by tau. Okay. It's the same thing here. E divided by negative T divided by tau. Okay. What about this one here? I told you what value should have here, okay? This one, if I go back to what I explained, I note, yeah, I note actually equal Vs minus V0, V naught divided by R, okay? In this example, I think Vs was 20. Let me remember what was V naught. V naught here, which is 10, and the resistor was 30, okay? So 20 minus 10 divided by 30, okay? 30K. So the calculation is 1/3 millisecond. This is I know, okay? That's exactly what I did. So now I know the voltage. So now I was able to calculate the voltage across the capacitor. I know the voltage here, and I know the current, okay? This is the equation of the current, this is the equation of the voltage. Is that difficult? Okay. Yes.
It doesn't matter if the VS2 is less than VS1 or greater than VS1. The same formula applies.
The same formula, yeah, this is a very good question, but the same formula applies, yes. So now, yeah, so this is the initial value. I started from 10. That's why you look here. I started from 10. This is the initial value. And it's gonna charge until 20. Okay. Same thing here. I started from 1/3 for the current. The current is gonna go to 0. Okay. Let's have one more example. Okay, guys. Let's have one more example. For example, here, let's look at this example here. I give you this circuit, as you see here, and then I tell you, let's see here what about. I need to tell you something to be able to calculate the initial value. So here, look what I said here. The switch in the circuit loop is closed at time t equal to 0 after being open for a long time. So I'm telling you, this switch was open for a long time. And then I wanna calculate I wanna know what's gonna happen once I close the switch. I wanna know what's gonna happen. Okay? So it was open for a long time. So that means the initial value for the capacitor is actually the steady state voltage when the switch was open. Okay? So if you see here, yeah, this here, the switch was open for a very long time. Okay, so what do you think? What should be the voltage here across the capacitor? 0, because there is no source here. There is no source. Okay, or you can imagine, if you are confused, you imagine you have a battery here with 0 volt, which is the short circuit anyway. So it's very clear here because I don't have any sources here, and it is in a steady state. Okay, so the voltage should be 0. So the initial value is 0. Is that okay? So always in this question, I tell you, it was open for a long time and then I connected it. Or it was connected for a long time and then I opened it. Why I tell you that? Long time here means it was in a steady state, and this should help me to find the initial. Always we do that. Okay? They help me to find the initial value. Anyway, so now I already know the initial value. So this one initially, before we connect the switch, as you see here, before I connect this switch, so this one was 0. The initial value was 0. Is that okay? So now I'm gonna connect the switch. Okay. So now I need to find. I need to solve this circuit here. It's very clear. This circuit is very different from the only circuit I know. That's why I'm telling you this topic looks so difficult. You have equation, exponentiation. You have a differentiation equation. It looks difficult, but it's not, because we are going to work only in one circuit. Okay, for sure this circuit looks different from. This circuit looks completely different from the circuit. From the circuit we already have the solution. Okay, so what should I do now? I already told you how I can make this one similar. How I can make this circuit similar to the circuit I already know its solution. How I can do that? As I told you, I need to find Thevenin for this part here. Okay. How can you find Thevenin for this part? Okay. Okay, so I'm gonna explain it in details, okay? So for example, here you have, that's what you have resistor, you have here, for example, VS, and you have here, I think, you have another resistor here, you have a capacitor, and you have a resistor this way, is that right? This is correct, right? Let me see. Yeah, so here I'm gonna R1, R2, R3. Okay. R1, R2, R3. Is that okay? So all what I have to do, I have to find Thevenin for this part. Once I find Thevenin, I'm done. So I have here R Thevenin, and then I have here B Thevenin, and then I have a capacitor. That's it. And then I can apply the solution for this circuit. Very easy, right? But how can you find Thevenin for this part? How can I find it? Okay, let's start. Let's start, for example, R Thevenin. Okay, so in case of R Thevenin, as I told you, yes, I can calculate the equivalent resistance from this side. It was wrong to do in the test because in the test we had a dependent source. You can do that if you have a dependent source, but this time we don't have dependent source. So it has to be, in order to do that, I have to do this one short circuit. So now it becomes R1, it becomes R2, and then short circuit this way, and then you have here R3, and then I want to calculate the equivalent circuit this way. Okay, so it's very clear. You can see these two are in parallel. They are in series with this one. So here R Thevenin should equal R3 plus R1 in parallel with R2. Any question? Okay. So now I'm done with R Thevenin. Now let's do V Thevenin. So as you know, I need to open the circuit. This is here. This is V open circuit. So I need to find the voltage across here. But I need to return the source here. Okay. So I need to open the circuit this way. I need to find the voltage across this one because this one is actually V Thevenin. Okay. So if you see here, it's very simple. I know there are very small things that confuse the student. Okay, so here I know all the current will come here. Okay, what about this resistance? Can anyone answer me? What about this resistance? You just ignore it. Why?
Current.
No current, because there is no closed loop. Okay, there is no closed loop, no current will come here. It's like it's not connected. Okay, so it should be a closed loop. There is no closed path. There is no closed path here. So the current cannot come this way because it's this open circuit. Anyway, so now, so that means because there is no current here, the voltage here is similar to the voltage here. It's the same voltage because there is no voltage drop. What makes a voltage drop across any resistor is a current. Okay, so if I can find the voltage here, should equal to the voltage here. Okay, because there is no current here. So all what I need to find now is the voltage across this resistor. Okay, what is the easiest way to calculate this voltage across this resistor? Voltage divider. This is the easiest way. For sure, you can make Kirchhoff voltage law, whatever, but the easiest way, just the voltage divider. So you can say here, V Thevenin equal Vs times R2 divided by R1 plus R2. That's it, it's done. Once I have the circuit this way, I can just plug in, I can just plug in the parameters I have in the solution, solve that's it. Okay. I already have the initial value. Okay, so that's what I did here. Yeah, that's what I'm explaining here. So I found R Thevenin equal to this value. I found V Thevenin equal to this value here, voltage division. And now the circuit becomes, you have R Thevenin, V Thevenin, and then you have C. Okay. And also you have V naught. So V naught equal to 0, the initial value V naught equal to 0, V Thevenin equal to 6 volt, tau equal R times C. Okay, so this R Thevenin times C is tau. Okay, so you have everything now. You can plug in the equation, and then I find the equation this way: VC, the voltage across the capacitor, equals C times 1 minus E. So you can see there is one part here was removed because there was one part related to the initial value. Okay, the initial value is 0. So anyway, and this is the impact of the impact of the batteries. Okay? Anyway. So this is the solution. You can see VC should equal this one. Same thing. If you want to get the current I, if you want to get the current I, same thing. You can apply in the formula we have. Yeah, you can apply in this formula, okay, because you already know Vs is 0, Vs is 0, Vs here is 6, V naught is 0, R, I don't know what was R, okay, 20K, I guess. We found R Tiffany, R here, which is R Tiffany 20K, okay? So now if you want to calculate it, so it should be I naught should equal to 6 minus 0 divided by 20K, okay, whatever the value is. So it should be IC equal 6 divided by 20K, E negative T divided by tau. I don't remember what was tau. Tau is equal R times C. So here when we calculated tau, R times C, it was 0.2. Okay. By this way, I know the current IC. Is that okay? The test will be one of these examples, this one and previous ones. Okay. So here I can add, okay, so now, but wait a second. Someone can ask me, but you are focused so much on the capacitor. What about the other? Because if I can find the voltage here and the current here, I can find everything else. How? I'm going to tell you how here in this. So here I'm giving you. Also need to solve this one for the test, okay? Here I'm asking you find IC. That's easy. Once I have the voltage, I already calculated. You can differentiate this one, but you don't need to differentiate. You can just use the formula. You can find IC. I need to calculate IC. Okay. Now I need I and I need IS. So here I'm asking you to calculate. This is like a homework. Okay. Here I'm asking you to calculate. I already calculated IC. IC is here. Yeah, I calculated this way. Okay. Down here was 0.2. Okay. So this is IC. Look here. V or I are not a number, but it should be equation in the time. Okay, because it's different from what we did before. This one should be function in the time because it takes some time to charge. So don't expect the voltage will be 7, 8, 9. No, it's gonna be similar to what we did here. It's gonna be equation in this one, function in time. I also should be function in the time. So now what I'm saying is I already know the voltage here. I already know the voltage across C, and let me solve it here. Just I want. You have Vs here. You have here R1. You have R2. I'm gonna go back to the original circuit. Okay. Here you have R3, and then you have the capacity. I already know VC and IC. These are nodes. Okay. So now I'm asking you, can you calculate IS? And can you calculate I'm gonna call it I2, for example. So that's what I'm asking you. Can you calculate IS, I2? I already know the current here. IC. First of all, IS is equal to I2 plus IC. Make sense? Kirchhoff current law. Okay, that means my problem is an I2. Once I find I2, I'm done because I already found IC. But again, it's not a number. It's going to be equation in time. E to the T. Okay. So now the question, how I can find IT? Okay. IT is actually the voltage here. Sorry, I2 is the voltage here. So I can say I2 equal V2 divided by R2. That okay? Ohm's law. How I can find V2? I'm gonna make a small trick. Okay, I will redraw this circuit. So this circuit actually we have here R2, and then I have here R3, and then I have a capacitor this way. I already know VC is known. Okay, why I redraw this way? Why? What I want to tell you? What I want to say here? Why you redraw this way and you think if I redraw this way it becomes easy? Well, why do you think so? Again, I'm looking for V2. My problem is here, V2. Yes, they are parallel to the same voltage. That means voltage here also equal to VC. Okay, that means VC should equal the drop across R3, which is V3 plus VC. I already know VC. Is that okay? What about V3? V3 is actually IC times R3 plus VC. So I already know IC, I already know VC. Okay? Sorry, this V2. Very easy, guys. So what I'm saying here, the voltage drop across these two, resistance and the capacitor of these two, it's the same voltage drop here. I already know the voltage drop here and I know the current. Is that easy to calculate the voltage drop here? Yes. Just it is IC times R3 plus VC. And this will be equation on time, E to the power of something. Okay. Once I know the voltage drop here, I divide it by R2, okay? And this will give you the current, I2. Any questions? If I bring something like that in the test, you can solve it. Let's see the next example. The next example here. In next example, I have a circuit like this one, and let's see what I told you here. The switch is closed at time t equal to 0 after being open for a long time. I'm telling you, this switch was open, so the circuit was, this one was open, something like that. It was open for a long time, okay? And then at time t equal to 0, I closed it. I closed it at time t equal to 0, okay? So when this one was open for a long time, what was the voltage here? This one, what was the voltage? Vs. And this is your initial value. Okay? So my initial value is equal to Vs. This is number one. This is at time t equal less than 0. Here, 0 when I close the switch. This is 0 start, and when I close the switch. That's why I say t less than 0. That means before I close the switch, this one was open for a long time. And the phrase long time means it's a steady state. Okay? So the voltage drop here is actually equal to Vs. Yes. Okay. Now I will start from now. Now I will close the switch at time t is equal to 0. I will close the switch this way. Okay. So now all what you need to think to solve these problems. Number one, I need to find the initial value. I already found it because this one was open. This switch was open for a long time. So the voltage here equal to Vs. This is number one. Number two, you need to mix a circuit similar to the circuit we already solved it. You get what I'm saying? So it's very obvious this is perfect because you have it's not the same. Don't make a simple mistake. You cannot just add R1 plus R2. You can't do that because you have to make sure here, right? It's different from what we had before. Okay? Because if this one open circuit, yes, I would say yes. But this one has a short circuit this way. Is that okay? Anyway, so again, the easy way to do it, I can again do also Thevenin, and I can calculate Thevenin this way to calculate R Thevenin and V Thevenin, okay? And that's what I did here. That's what I did here in this solution. I calculated here so here for this part here, I'm going to calculate R Thevenin. So as you see here, to calculate R Thevenin, I have to make this short circuit. This source here is short circuit. This one already short circuit. This one, okay? So when you calculate the resistance here, okay, this also confuses too much. Look at R1. R1 is already short circuit. So there is a short circuit here around R1. So you cancel R1. So if I look from here, what resistance you will see from here? Only R2. So if you have a battery, this is the way I think about it. If you have a battery and you connect the battery this way, okay? All the current will come here, okay? So what resistance this battery will see? Only R2. Because you need this one is cancelled because there's a short circuit around, okay? So R Thevenin is equal to R2. What about V Thevenin? Okay, so as you see here, V Thevenin is the voltage source here across the voltage drop here. Okay? You can see here because the current will go this way, there is no current because there is no set back here, there is no loop, no back. So here, there is no current here, okay? So the voltage drop here is similar to the voltage drop, which zero, short circuit. Got it? The voltage drop here is same like this one. Why? Because there is no current here, there is no drop in the resistance here. So the voltage drop here is equal to this one. And because this is a short circuit, the voltage drop here is equal to zero. So V7 is zero. Okay. So now V7 is a zero, okay, and then I have R7 and then I have C. So now I can just apply, now I can apply the solution. I have the initial value. I already know R7 is equal to 2, which is R2, as I told you. We have V7 is equal to 0. You can just plug in here, and then you can, after you plug in these values in the solution you will already have, you will find this is the final solution. When G less than 0, before we connect the switch, the voltage across the capacitor is 10. When I close the switch, the voltage across the capacitor is actually this one. This is the one I calculated here. Is that okay? What's interesting here? The interesting here, the steady state, what is the steady state value of the capacitor here in this case? 0, right? Because we have only the transit part. Because the battery is 0. You got what I'm saying? Because this battery, V7 is 0. Okay? So that means in a steady state, the voltage here across the capacitor is 0. Okay? Equal to V7. So what's gonna happen here is this one is gonna discharge. Not a charge, discharge now. Okay? So this one initially it has 10 volts, and now because of the way we connect the circuit, this one is actually here, the capacitor is gonna discharge here, and now becomes 0 after that. Okay. Any questions? So in test 2, I will give you problem like this one. You need to only study the examples here. I can't make it easier than that. Okay, it will be very close to this one. I will quickly give you the formula for the voltage and for the current. Although this example, my main focus was only on the voltage across the capacitor and the current across the capacitor, but similar to what I explained here in details, you still be able to calculate the voltage and current everywhere. You get what I'm saying? So because this is the problem, once I know IC and I know VC, you should be able to calculate the current everywhere. So I can actually in the test, I may not only ask you to give me IC, okay, but I can also, similar to this example, give me the voltage drop here. You should be able to calculate everything once you know IC and VC. Yes.
So in the last example, the current will be flowing from the capacitor up to R2.
Yes.
And down to the,
Yeah. For a short period of time.
for-
This is because initially the capacitor has a charge. That is why initially the capacitor has a voltage of 10 volts initially, because it has a charge. Once it discharges, it's going to lose all its charges, and now it becomes 0 volt. Anyway, so I will go back to these 2 examples. They are very simple examples. So let's look at this very simple circuit here. In this circuit that you see here, you have this switch was connected for a long time, and then I'm gonna open it. Okay, so this switch was connected for a long time, and then I'm gonna open it. Because this switch was connected for a long time, what is the initial values across the capacitor? Equal to 2 volts, similar to this one. Makes sense? Because they are in parallel. So this one was connected for a long time. Because of that, because it was connected all the time, so the voltage drop in has to be 2 volts. It's not 8. Okay? Because any voltage source, the voltage drop across it has to be constant, which is 2 volts. So from here to also it has to be 2 volts. You understand what I'm saying? So when the switch is closed, so the voltage drop here is actually equal to 2 volts, the initial. And then, so the initial value here is 2 volts. And then I will open it. Okay, once you open it, this is very easy. You don't need to do anything. This is similar to the circuit we calculated its solution. But I already know the initial value, which is 2 volts. Okay, and that's what I did. So the initial value is 2 volts. Now I'm going to calculate. Here R and C. So here this is R 10K, and this is C So now I can calculate tau, and then you can just plug in the equation, and then after that, after you plug in the equation, you will get this voltage, straightforward. Okay. Sometimes we add, here in this question, I tell you, okay, so this is the voltage, this is the voltage across the capacitor, okay, function in time. After that, I tell you, okay, can you tell me what is the voltage after 50 milliseconds? Okay, you can just plug in here. This is a formula, right? So this is a formula for the voltage across the capacitor. Here I'm asking you, what is the voltage after 50 milliseconds? Okay, so I'm gonna plug in time here, it's 50 milliseconds, and then I count it's 5. It's 27. Because this one is gonna short until 8. خلاص بالي with 8. It's gonna short until 8. But after 50 milliseconds, it was only 7.5. But it's still keeping charging. Okay? So if you, I have a nice figure here. Yeah, if you look at the figure, we start from 0 here, and then it's gonna charge. If the initial value is 2, we start from 2, and then at time 0, and then it's gonna charge until it becomes 8. So here I'm asking after 50 milliseconds, it's here. It didn't reach to 8 yet, but it was 7 point something, 7.5. Is that okay? The last thing here, I'm gonna, next example here, look here guys, this example is identical to the example I have just explained right now. It's exactly the same thing, but there is a small difference. I just want to tell you about, but I'm not going to ask the examples about it, but I want to tell you about it. Okay? So here, this circuit is exactly similar to this circuit. This is example is a textbook, but there's a small difference. The small difference is here, I'm going to connect the switch. I'm going to open the switch at time equal to 0. Okay? In the next example here, I told you I'm going to open the switch at time equal to 50 milliseconds. So the switch is not going to open at 0, but it's going to open at 50 milliseconds. That's what I'm saying. So that's why if you look at this solution, so what's gonna how this will impact the solution? Nothing. All what's gonna happen here, instead of you start charging from 0, I'm gonna start charging from 50 milliseconds. So that's why you see it here. Look, see the difference? Because actually the switch, I open the switch here, open the switch at this time, not at 0. I open the switch here. You get what I'm saying? So although most of the time we couldn't make disturbance. You make disturbance when you close the switch or when you open the switch, you make disturbance. Usually we make disturbance at time equal to 0, usually, right? But sometimes, okay, I can make it at any time other than 0. But in this case, we need to modify the equation. We have very simple modification. Remember, in the equation, this was t. Now it should be t minus t0. I'm going to start the disturbance from here. You get what I'm saying? So what I'm saying is that the equation I explained, you can use. Always look at this equation here, guys. Here, always the equation here started from time t. It has t, okay? Because the disturbance is going to happen at time 0. If I give the disturbance is going to happen after 2 milliseconds, 3 milliseconds, all what you have to do, the same equation, but instead of having here t, it has to be t minus, replace t by t minus the time, okay, 2 milliseconds, the starting time. Is that okay? So just I want to bring this to your attention. I'm not going to ask about it, but just keep in mind all what we have done so far. The disturbance for this equation, disturbance is going to start at time t equal to 0. If the disturbance happens at any time other than 0, it's again the same equation, but it's going to be t minus the beginning time. And the impact is very little impact. Instead of starting, look here I started charging from time 0. But here it's exactly the same thing, but I'm going to start because the switch is going to be open here at 50 milliseconds. So it's going to start here. Okay? Everything is the same. So this one will go to 8 as well. So the solution, everything will be here the same. Okay? Yeah, this is the equation here. Okay. Everything you are going to charge until 8, everything is still the same. Okay. Any question? So next time I will start. I'm gonna repeat what I said today. Almost I will repeat everything, but for when you have a coil, there are very small changes, but everything is the same. Okay. I will start with the certain circuit, and then I will show how can we find the solution. Then I will do almost the same thing, but for inductor instead of capacitor. Same idea. Everything is okay, guys. Any questions? We can start the brief now.